Welcome to The Explainer. All right, today we're going to tackle one of programming's most, well, let's call it a double-edged sword. Inheritance. Get it right and your code is beautiful. Get it wrong and you've got a tangled mess on your hands. So let's figure out how to use this thing the right way.
Okay, let's just get this out of the way. There's one rule every single programmer learns, usually the hard way. Duplicate code is just plain evil. I mean, think about it. The second you copy and paste some code, you've basically created a landmine for your future self. Need to make one tiny change? Now you're on a scavenger hunt, praying you find every single copy. It's a nightmare, plain and simple.
So how do we tackle this? Here's the game plan. First, we'll nail down the core idea, the is-a relationship. Then we'll see it in action and check out its real power. After that, we'll cover the really important rules you gotta follow. Then we'll get into the dark side, the inheritance trap, and finally look at what to do when is-a just isn't the best fit.
And the classic fix for all that evil duplicate code? Yep, it's inheritance. At its heart, it's all about creating what we call an is-a relationship. You know, a dog is an animal. This simple idea lets the dog class just automatically get all the stuff the animal class can do without you writing a single extra line of code for it. Pretty neat, right? Right. Let's dig into that is-a thing a bit more. Honestly, the best way to think about it is like building a family tree, but for your code. So it's a pretty simple setup. You've got a parent class, we call it a superclass, and it passes down all its traits, its methods and attributes, to the child class, or subclass. That child gets everything the parent has. From there, it can just use those things as they are, or it can add new stuff, or even change how the old stuff works. That's where all the flexibility and power really comes from.
Okay, so theory's cool and all, but what does this actually look like when you're writing code? Let's check out how this simple idea can build some seriously useful tools.
And hey, inheritance isn't just for the classes you build from the ground up. You can actually take Python's built-in tools, like a list or a dict, and basically give them superpowers. For example, maybe you need a list that can search for your contacts by name. Easy. Just inherit from list and add your own custom search method. Or what if you want a dictionary that will scream at you if you try to add a key you've already used? Just inherit from dict and change how it behaves. It's a really elegant way to add new features.
But, with great power comes great responsibility. If you're not careful, this double-edged sword can make a real mess. So that brings us to the rules you absolutely have to follow to keep things clean.
So the most important rule, the golden rule, is the Liskov substitution principle. Yeah, I know, it sounds super academic, right? But the idea is actually dead simple. It just means that if you have a child class, you should be able to drop it in anywhere you'd use its parent class, and the whole program should just keep working. No explosions, no errors. A square should be a perfect substitute for a rectangle. If it isn't, well, that's a sign your whole model is broken.
And here's a quick little mental check you can do to see if you're on the right track. First, ask yourself, does it make sense to say, my child class is a type of my parent class? So, a square is a rectangle. Yep, that checks out. Then flip it. Is a rectangle a square? No, not always. Since it only works one way, inheritance is probably a good choice here.
And this is the part that trips people up, but it's so important. If that test works in both directions, then you should never, ever use inheritance. It's a huge red flag that these two classes aren't really parent and child. They're more like siblings, and forcing that inheritance relationship is just asking for a confusing, fragile mess down the road.
Okay, so we know the rules. Now let's step into the danger zone. This is where things can get really complicated, and where even experienced pros get themselves into trouble.
This quote just nails the general vibe around multiple inheritance. When a class inherits from more than one parent, it's something you really need to handle with care. 9 times out of 10, there's probably a better way to do what you're trying to do.
And the biggest reason for all that caution is this beast, the diamond problem. Just picture it. You have a child class inheriting from 2 parents, but both of those parents inherit from the same grandparent. So when the child calls a method from that grandparent, which path does it take? Which parent's version gets used? It's ambiguous, and it can cause methods to get called twice or even not at all. It's a total mess.
But thankfully, Python has a really clean way out of this, the super function. When you use super, you're not just vaguely calling a parent. You're telling Python, hey, go look at the official method resolution order, or MRO, and figure out the next logical method to call. The MRO is this pre-calculated path that makes sure every method in the chain gets called exactly once in the right order. It just solves the diamond problem. All this complexity kind of leads us to a really important realization. Maybe, just maybe, the is-a relationship isn't always the best tool for the job. So let's look at some more modern, flexible ways of thinking.
In Python, we have this philosophy called duck typing. The idea is that we don't really care about what an object is, like its official class name. We care about what it can do. So if an object has a .quack method and a .walk method, well, for our purposes, we can just treat it like a duck. We don't need to force it to inherit from some official duck class.
And that brings us to the biggest alternative of all, composition. Instead of saying a car is a vehicle, we switch our thinking and say a car has an engine. See the difference? This has a relationship is way more flexible. It lets us build things with loosely connected parts, so we can do things like swap out the engine in our car without having to redesign the entire car.
So your modern programming toolkit has a bunch of great options. Composition is your workhorse for building big things out of small, interchangeable parts. Mixins are like little reusable feature packs you can bolt on to any class to give it new functionality, like logging. And interfaces are basically a formal contract for that duck typing idea. They define what an object must do, without getting bogged down in how it does it.
I think Joe Armstrong, the guy who created the Erlang language, said it best with this quote. Sometimes with inheritance, all you want is one little piece of functionality, the banana. But to get it, you're forced to drag along the entire class hierarchy, the gorilla and the whole jungle. He even called it the inheritance tax. So that leaves us with one final big question. The next time you sit down to write some code, are you going to ask what your object is, or are you going to ask what it has? Just shifting your default from inheritance to composition, that could be the single biggest key to unlocking simpler, more flexible, and honestly more powerful code. Hope this helps you handle that double-edged sword a little better. Thanks for tuning in.